This lesson is on finding inverses of functions. The objective is to determine the inverse of a function and identify the domain and range of any inverse function. Some of the vocabulary we're going to come across is inverse of a function, horizontal line test, and domain and range. Let's start off with a little bit of a review. Here we're given the function f of x equals negative 4x cubed plus 2x minus 1, and I ask you to find what f of negative 1 is. How do I solve this? You're correct. Wherever I see an x, I plug in negative 1. This negative 1 is known as what's called the input. You're subbing that into the equation. And what you're getting is the result, which is considered the output. In this case, it's 1. If you look at the graph of negative 4x cubed plus 2x minus 1, it looks something like this. That negative 1, 1 creates an ordered pair, an input-output pair. We know that as a point along the graph. How does this relate to inverses? Well, what an inverse of a function is, given any coordinate pair x comma y, the inverse of the function, or this relation in this case, is y comma x. You switch the ordered pairs. The notation we use is this, f inverse of x. So what does this mean in terms of domain and range? Well, what happens is the domain of the function, the original function, is now the range of our inverse. And the domain of our inverse is now the range of our original function. I know this sounds confusing, but let's look at an example here. Here we're given some relation, some set of ordered pairs. To find the inverse, all I have to do is simply switch the coordinates. So it's this. Notice how our domain in the original was negative 1, 0, 4, 6, and negative 3. That is now the range of our inverse function. And if you look at the range of the original, which in this case was 2, 3, negative 2, 1, and negative 1, that is now the domain of our inverse function. So this is the example. Now, let's find the inverse function. In this case, we're going to find it by graphing. And we're going to notice some unique properties about inverses and their original functions. Here we're given f of x equals negative 2x plus 3, and I ask you to find the inverse by graphing. Let's first set up a table to see these ordered pairs. Pick some values. Here I'm picking values between negative 2 and 2. If I plug in negative 2 for the function, my answer is 7. If I plug in negative 1 for x, we get positive 2 plus 3, which gives me 5. If I sub in 0 for x for the original function, I get 3. And if I sub in 1, I get 1, and if I sub in 2, I get negative 4 plus 3, which is negative 1. So there's my order pairs, negative 2, 7, negative 1, 5, 0, 3, 1, 1, and 2, negative 1. If I switch the table around, I create the inverse function. So it looks like this. Now my order pairs are switched. My domain is now my range, and my range is now my domain of the inverse function. Well, let's plot these points and see what happens. If you take a look at the original function, this time it's going to be in red. Plotting those points in the table, you get a diagonal line like this. And it makes sense because it's the y-intercept started at positive 3. And if you notice, we have a slope of negative 2, down 2, right 1. So here's our diagonal line of the original function. If I plot the points of the inverse function in the other table, switching the coordinate pairs, you get a diagonal line that looks like this. One thing you notice is there's some symmetry going on between these two lines. Can anybody recognize the symmetry? It's kind of hard to see right away, but if you divide the paper in kind of diagonally, this is actually the y equals x line. It goes through the origin. And in fact, this is one property of inverse function, is that inverse functions are always symmetric about the y equals x line of any of the original functions. Let's flash back to semester 1 when we actually originally started talking about functions. This was in chapter 1. We talked about a special test. This test, called the vertical line test, told us whether the graph itself was in fact a function. So what we did is we placed a vertical line anywhere throughout the graph, and if it hit twice, we said it was not a function, and if it hit only once throughout the entire graph, it is a function. So if you look at these 4 examples, in the first one, if we place a vertical line, you notice that we hit twice in 2 areas along this graph. So in this case, this would not be a function. If you look at the second example, again, throughout a circle, we hit twice, So therefore, this would not be a function as well. If you look at the third and fourth case and place a vertical line throughout those graphs, you notice it only hits once throughout the graphs. So these two last cases are considered functions. Now, how does this relate to inverses? Well, we do something very similar to inverses of functions. In fact, we use what's called the horizontal line test. Here, this is the graph of f of x equals x minus 1 squared minus 2. It's a parabola. It's a quadratic function. If you notice right away using the vertical line test, placing a vertical line throughout the entire graph is only going to hit once. So this itself is a function. But what the horizontal line test does for us is it determines whether the inverse is a function. So what it says is if we place a horizontal line, as shown here, if the horizontal line now hits twice throughout the graph, we say that the inverse is not a function here. But the original function is a function. Let's get to our last objective of the lesson. This is finding the inverse of a function algebraically. We already explored finding the inverse of a function graphically. Now let's look at the same exact example, but focus on finding it algebraically, actually finding the equation for this inverse. So here you notice we're given the same function as before when we looked at it graphically, negative 2x plus 3. To find the equation of the inverse, you need to follow three basic steps. The first step is to replace f of x with y. So if it's written in function notation, just simply replace f of x with y so it looks like this, y equals negative 2x plus 3. The second step is simply switch the variables. How do I do this? Well, you make x y and you make y x, so it looks like this. So now our equation reads x equals negative 2y plus 3. The very last step is just solve for y. This is something we did in Gateway 1. So solving for y here, if you look at the first thing we want to do is isolate y by itself. So we got to get 3 to that other side. In this case, since it's positive 3, let's subtract 3 to both sides. So now we get x minus 3 equals negative 2y. And to solve for y, all we have to do is divide by negative 2. We do that to both sides. And what you notice is it cancels on the right-hand side, which gives us our end result of y equals x minus 3 all over negative 2. This is the inverse of that function. So, I want you to try this one. Follow those three basic steps that we had before in the last example. Pause the video, and we'll work this out together in a little bit. So, remember the first step. Replace f of x with y, so it becomes y equals x minus 1 all over 2. The second step you remember was to switch the variables. Well, switching the variables here would now read an equation of x equals y minus 1 over 2. The question is, how do I solve for y here, because that's my third step? Well, if you notice, the first thing we want to get rid of, we want to get rid of this 2 on the bottom. And since it's dividing by 2, the best way to get rid of it is to multiply 2 to both sides. It will cancel it on the right-hand side, which gives us 2x equals y minus 1. And the only last step we need to do to solve for y is just add 1 to both sides, and we get our end result of y equals 2x plus 1. This is the inverse of our original function. So, that concludes our lessons on inverses of functions. I want you to attempt some of the Google questions below. They are multiple choice. Try your best. And come to class tomorrow to practice these inverses. Hope you enjoy your night.